Alrighty. Good afternoon. My name is Mitchell Lapierre, and this is going to be my walkthrough for the graph algorithms assignment. I'm going to be walking you through Dijkstra's algorithm and Kruskal's algorithm, showing the code first, and then explaining what each part does. I grouped the tasks together, so Dijkstra's task goes first, followed up with Kruskal's task. So let's get started here. For task one, here's the part of the code where I build the example graph of nodes A, B, C, and D. This creates a directed graph where each edge has a weight. And then up here, I'll show you the Dijkstra function. So the distant map is to store the best costs for each node. The parent map is to rebuild the path, and then the priority queue is so the cheapest node always comes out first. Every time I relax an edge, I check if the cost can be improved. If it can, I update the distance and parent, and that's pretty much the core of Dijkstra's algorithm, as seen below with task one, from A to B, and the total weight, and so on and so forth. And then for task three for the emergency routing, as shown here, Dijkstra's algorithm is going to be used again, but for a small emergency response graph. Here's the code that builds the graph as follows. The edges represent travel times, and the Dijkstra algorithm will be ran the same as in task one. And as below, you can see what the output is with the the fastest route from hospital A to the accident, total being 5 minutes. So moving on to Kruskal's algorithm. Pull that up here. So for task two, here's the section where I list all my edges, and then I will run Kruskal MST, which uses the sorting to process the small edges first, and then unit find to avoid the cycles. This is what keeps the MST from forming loops. And as you can see here, here's the output for task two, showing from A to C, C to D, A to B, with total weight. So with that, I'm going to head on to task four. And this task uses the same algorithm, but the graph is a small power station setup, as shown. So the edges will look like this, and the Kruskal picks the two cheapest edges and avoids the expensive one that would create a cycle. And the output shows station 1 to 2, 3, station 2 to 3, 4, total cost being 7. So this is what I believe exactly what we expect for an MST. So for the complexity summary, for Dijkstra's algorithm, time complexity is big O parentheses V plus E parentheses log V, because it uses a priority queue and relaxes edges. And then for Kruskal's algorithm, the time complexity would be big O parentheses E log E, because it sorts the edges and uses union find. So both algorithms are efficient and widely used. Dijkstra is good for routing and navigation, while Kruskal's is good for building cost-efficient networks. This wraps up my walkthrough for tasks 1, 2, 3, 4. Thanks for watching, and let me know if you have any questions about the implementation. Thank you.